Hello, I'm a PhD student from the National Center for Nuclear Research, and I will tell about the AGN selection that was performed by our group. So the importance of searching for the type 2 AGNs was already mentioned, so I will skip this part. We were searching for the AGNs in the NEP deep data, and we used the supervised learning algorithm. So in this case, we needed the labeled sample with the known classes of objects. However, the spectroscopic data for the NEP deep survey is very small, and because of that, we used the data from the NEP wide as our training sample with the spectroscopic confirmation by the Subaru spectrum. For this task, we use the support vector machine algorithm, which is the supervised learning algorithm. The main idea is to map the data from the input parameter space, where the separation between classes can be very difficult or even impossible, to the high-dimensional feature space, where these additional dimensions are created in an artificial way by taking combinations of the input parameters. And in such high-dimensional space, the separation between classes then becomes possible. What is important in the case of this algorithm is that exact mapping between these two spaces is not needed for us. We can use just one of several types of functions called kernel functions that will describe us this mapping. And SVMs were already used for the AKARI NEP deep data by Alexandra Solarz, Agnieszka Polo, and others for the star galaxy separation. In this case, we use the modified SVM algorithm called the fuzzy SVM algorithm. It allows us to incorporate, give each object from the training set the different importance in the process of creating of this separation hyperplane. And in our work, we use the measurement uncertainties as such importances. So objects that were measured more precisely, objects from the particular class, were used as more important entities in the creation of this separating hyperplane. And as the result, we obtained a more better physically motivated classification. To evaluate the performance of the algorithm, we needed to use slightly different metrics than it usually people used. For example, accuracy, because we had the we had an unbalanced data sets here. And because of that, we used Cohen's kappa and Matthews correlation coefficients, which are quite similar metrics, and they show you the agreement between two raters, where one rater is the output of our classifier, and the second rater is the set of the spectroscopical labels. We also use the precision and recall, which in our case is the purity and completeness of the output AGN catalog. And we also use the area under ROC curve, where this ROC curve shows the performance of the binary classifier when the discrimination threshold just varies. So to summarize, we use the fuzzy SVM binary classifier, which was trying to separate AGNs versus not AGNs objects in the AKARI NEP deep data. We use the scikit-learn implementation of the SVM algorithm. As a training data, we use mainly data from the AKARI NEP wide, kernel functions that maps the data into the high-dimensional space where the sigmoidal and the radial basis function, and in the training process to tune the parameters of the SVM, we were maximizing this metric, the area under ROC curve. And because of the small amount of data, we didn't separate the additional validation set, we just used the 5-fold cross-validation during the training. So first thing that you should do when you train your classifier is to think about what is the best representation of the data for your particular task. So in our case, we need to remember about the several things. First of all, we have strongly decreasing statistics when we are going to the passbands that represent the longer wavelength. On the other hand, we also need to remember about the information content of particular passbands. And we also need to remember about the very small amount of data, and this data is also not equal for particular classes. So in our case, we used the several strategies. First strategy was the statistic preserving strategy. So we just trained two different classifiers. One was using only near-infrared passbands, fluxes and colors, and the second one was using only mid-infrared passbands. So in this case, we were able to trace objects which were visible only in one of these parts of the spectrum. We also used two physically motivated features. One of them was the classical 6 colors feature space made of colors from the neighboring filters. And well, it gives you the best possible probably information, but again, now we have low statistics because we need objects which were measured in each narrow passband. We also used the same idea but with the wide passbands in the mid-infrared, and we also used the mutual information minimization technique, which gives us features that are the most independent features. So we also created such independent feature sets. And here you see the result of the training. So the radial basis function kernel was much better than the sigmoidal one, so I will show you only this one. And here you see the results. This one is actually quite surprising because the classifier that was trained only on the mid-infrared data showed the worst results, and it shouldn't be that, but it's surprisingly near-infrared is very important for the mid-infrared, at least for SVM, to classify the objects properly. The ROC was maximized during the training, so it has the highest values, and the recall or the completeness of the AGN catalog is indirectly optimized when you maximize the ROC area. The next thing that you should think about is the extrapolation of your classifier, because in the case of the supervised learning, the algorithm will only learn as much as you will teach it, and it extrapolates really badly. However, when you are limiting your generalization sample to the limits of your training sample, you still have these small corners in this n-dimensional space where you will have to extrapolate. So you need to check what is the output of such extrapolation, and you will know that you will get the better results, but you should know that you won't fail miserably. So we were dividing it to our data to the 70% of the training set and 30% validation with, for example, the faintest objects in the 2 micrometers passband. And here you see the results, and now the several metrics, they fall very bad in the case of most of our classifiers, but still 6 color feature set gives again the best results as it was previously shown. Previously shown here, it shows the slightly better result than other. So we choose the 6 color feature set, and as the result we obtain the output catalog. And now, because we have this small amount of data, we need to be as careful as possible, as conservative as possible. So now we can plot the Platts probability distribution. So it's a probability which is calculated on the basis of the distance of object from this separating hyperplane. And because we have the nonlinear classifier, this probability will be not normalized. So if you want to use it for some more advanced research, then you should definitely first normalize your Platts probability before you will use it. Here we just want to know where is the the range where we can just cut the probability without losing too much objects. So at first we got around 600 AGNs, and then we cut the probability on 0.7 to obtain just the most trustable objects. And we obtained the 275 objects. Then we compared it to the different AGN selection techniques. For example, we compared to the technique created by Lee and others in 2007. And it's based on the theoretical models. It assumes that you will additionally make some cuts in the 11 micrometers passband, and then your AGNs should fall into this upper right corner. And if you will apply this additional limit in S11 to our data, you will obtain the data set of these blue dots. So all objects will fall into this area. So our two methods are consistent. However, our SVM-based approach will give you the wider samples than the Lee method. So to summarize, we obtained a trustable new method for AGN selection in the AKARI data. The results were published in the publication of Astronomical Society of Japan. The code is available on GitHub, and now we are starting the collaboration with our colleagues here from the National Tsinghua University to search for obscured AGNs in the AKARI NEP wide with more advanced tools. Thank you.
Questions? Matt?
Now that you have a lot of new AGN that you have discovered here photometrically, can you give the coordinates, the names of them to TOFT so that they can put them on their list of possible DEMOS targets? We need more spectroscopic confirmation.
Yeah, sure, of course. No.
You did do.
No, we didn't.
No, we didn't publish them. Yeah,
but I mean, he's not going to go through the literature. You have to give it to him in a nice basket. Just send him an email so he can put it right into his DEMOS mask construction.
Yes, of course.
And we need to do this very quickly because NEP is coming out.
Tonight would be good.
Okay, so we can do it too.
Yes.
On Thursday.
Right.
Okay, we'll do. Sure.
More questions? Miguel?
So I didn't understand this very well. I want to ask how you measure the performance of your method.
How do I measure the performance of the classifier? Well, you are doing it in several steps. First, the best combination of the grid search is taken as the best classifier possible, and it is based on the maximization of this metric. So you take the highest value of this metric. Then you look on different feature set that can be passed to your classifier, and you took the most reliable one. And then you also need to check if the extrapolation, we did several of them, and in all of them 6 color feature set shows you the best results. So you need also to check when you have this small extrapolation outside the training set range, it won't give you very bad results because, well, then you will have a lot of outliers on the outskirts of your of the training range.
Any more questions? Tomo?
So I have a comment. How about inputting photometric redshift
Into the as an additional feature.
Yes, it is. So now Simon has very good photometric redshift, and then I don't know if you believe him or not. Let's suppose it's very good. Then, you know, in addition to the photometry, maybe you can include photometric redshift.
Well, it's always the case of a trade-off. On one hand, in machine learning, you want to be model independent. You just want to learn from the data. It's like the idea of the whole method. However, in the case of small amount of data set, I think yes, you can use set fittings and you can use the calculated on the basis of them of the photometrical redshift. Especially if we are looking for the type 2 AGNs and we are teaching our classifier on the spectroscopic data from optics, which are mainly the type 1 AGN. So yeah, I think additional data from other classifiers and or regressors and from the sets is probably a good idea.
Well,
Yeah.
what I see a little bit a delicate point here is that usually for the CD fitting you have a different accuracy of photometric redshift for galaxies and AGNs.
Right.
And this may introduce an additional bias, which should be careful about.
Yeah.
However, here Simon, he calculated the photometrical redshifts using the random forest. And well, here we do not have the real accuracy of the regression. So it's also...
But I would also expect a bigger spread for AGNs than for galaxies.
Well, yeah, of course. Sure.
And how do you estimate the uncertainties? I mean, it's for the errors that you get with the AGN fraction, for instance.
Can we estimate the AGN fraction from...
the uncertainties on the AGN fraction?
We do not compute AGN fraction.
You show that.
Okay, which one? This one?
No.
Okay, I will just skip.
Okay. Why?
Okay.
Maybe what you took for AGN fraction was AGN probability.
This one.
Which is,
Yeah.
No, it's just about, well, you have in this high dimension space, you have this separating hyperplane, and then you have the different distances of objects to this hyperplane.
Yes.
And then in this method, you are just fitting the sigmoidal function to this distance, and you are normalize it to have the probability. However, here you need to normalize it one more time, but it's not the AGN fraction, it's just the distance of the object.
we were thinking if we can interpret it as the AGN fraction in some sense, but this is...
No, it didn't work well.
Any more? Then, thank you.